The universe is astonishing in its scale. So many impressive objects are scattered across its vast expanses, and such gigantic distances separate us from the stars and distant galaxies. But it is as if nature once responded to all this admiration with "hold my beer", and it created the truly monstrous Ton 618, one of the most gigantic objects in the cosmos known to humankind. It is neither a star nor a nebula, but something far more impressive. It is a quasar with a black hole at its center. That black hole outweighs the Sun by an incredible 66 billion times. Today we are setting out on a journey to a true supermonster of the universe, the object Ton 618. And as usual, we will not do this only in theory. We will also find it in the sky, and with an amateur telescope we will capture the light from quasar Ton 618, a light that has been traveling toward us for 10.5 billion years. I'm Alex. It's the Night Sky Journey. Let's go! Without a doubt, Ton 618 has extremely interesting physical properties. Today we will certainly discuss them. And of course, Ton 618 has become very popular on the internet. You have probably heard of it. We will also talk about the reasons behind the hype surrounding it, but I would like to begin with the difficult path of its discovery. We will have to touch on many fascinating topics: the history of the discovery and study of white dwarfs, as well as the discovery of quasars and black holes. But first, don't forget to like the video and leave a comment. This will help the video avoid falling into supermassive black hole of oblivion on YouTube. This is the brightest star in Earth's sky, Sirius, in the constellation Canis Major. And this is how it looks through a telescope eyepiece. In 1862, the American astronomer Alvan Graham Clark noticed a faint little star next to Sirius. It was so close that it was lost in the glare of its bright neighbor. Clark had discovered the companion of Sirius, Sirius B. Both stars are bound by mutual gravity and orbit their common center of mass. In 1915, the spectrum of this star was obtained at the Mount Wilson Observatory. It turned out to be very small, very heavy, and very hot. Think about it, Sirius B is slightly smaller than our planet in size, yet in mass it is almost comparable to our Sun, about 1 ton of matter per cubic centimeter. Today we call such stars white dwarfs, but at the beginning of the 20th century this was only the second such object discovered in space, and the very fact of its existence seemed paradoxical. Classical physics couldn't explain why such a dense object didn't collapse under its own gravity. To understand the structure of white dwarfs, scientists simply had to wait for the creation of quantum physics. The theory of white dwarfs was developed only by the early 1930s. Now we know that they represent the final stage in the lives of small stars with masses no greater than about 10 solar masses. Our own star will meet the same fate. Today, the Sun calmly burns, gradually turning hydrogen into helium. In a few billion years, the core will run out of fuel, begin to contract, and the outer layers will expand. The Sun will become a red giant. Then, within the dense helium core, reaction converting helium into carbon will briefly ignite. When that fuel is exhausted as well, the Sun will begin shedding its outer layers. A beautiful planetary nebula will appear around it. The remaining hot core will begin to contract under gravity. As the temperature drops, ordinary gas pressure can no longer support it. It would seem that collapse is inevitable. But this is where quantum mechanics enters the stage. There exists the Pauli exclusion principle, according to which two electrons can't occupy the same quantum state. When matter inside a white dwarf becomes extremely compressed, electrons are forced into higher and higher energy states. This process creates a pressure that doesn't depend on temperature. It is called degeneracy pressure. So gravity tries to compress the white dwarf, while electrons packed to the quantum limit produce degeneracy pressure that resists the compression. An equilibrium state arises in which the white dwarf can exist. White dwarfs of various masses have been discovered in the universe from about 0.2 to 1.3 solar masses. But even here, there is a limit, the Chandrasekhar limit. If a white dwarf reaches about 1.4 solar masses, electrons can no longer provide sufficient pressure. Further collapse begins, leading to the formation of a neutron star. Despite their small size, white dwarfs, especially young ones, are very hot stars, with temperatures from 10,000 to 100,000 Kelvin. Paradoxical as it may sound at first, hot stars in the universe appear blue, while cool stars appear red. We can even see confirmation of this in everyday life. Here is a light bulb with yellowish light. We call it warm. Its color temperature is about 3000 Kelvin. And here is white, cold light, about 6000 Kelvin. Therefore, in the mid-20th century, one of the methods for discovering white dwarfs was the study of hot blue stars. Astronomers photographed star fields using special filters. Stars whose color was shifted toward the blue part of the spectrum were identified, then their type was determined through spectroscopic observations. Is it a blue giant or a white dwarf? This is what the starry sky looked like to me shortly before dawn in December. The constellation Virgo had just risen above the horizon. Today, it will interest us for several reasons. First, the brightest star in Virgo, Spica, is a multiple star system, and one of its components is precisely a blue giant. This is the spectrum of an ordinary star like the Sun, and here is the spectrum of a blue giant like Spica. Notice several dark lines in the blue part of the spectrum. These are hydrogen absorption lines, H-beta, H-gamma, and so on. They are also called Balmer lines. And this is the spectrum of a white dwarf. It resembles the spectrum of a blue giant, but the hydrogen lines are much broader, due to the enormous pressure on the star's surface. This is how scientists distinguish them. In front of you is the 70-centimeter Schmidt camera at the National Astrophysical Observatory in Tonantzintla, Mexico. Here a method was developed for sequential imaging in 3 different filters, which made it easier to identify blue stars and therefore discover white dwarfs. In 1957, using the same method, astronomers decided to investigate how blue and violet stars are distributed in our galaxy. For this purpose, they photographed a region of the sky covering 1360 square degrees. It was in this survey that an intriguing object from the constellation Canis Venatici was first noted under the number 618. From the name of the observatory Tonantzintla came the contraction TON. Thus, in 1957, a faint object of about 15.5 magnitude, TON 618, was catalogued and described as definitely violet. But its nature couldn't be determined at the time. This class of object hadn't been discovered yet. Let us return again to the constellation Virgo. Near the star Gamma, approximately here, lies another object important to our story, 3C 273. In the mid-20th century, radio astronomy was taking its first steps. Scientists noticed radio signals arriving from space and started recording and studying them. Early radio telescopes had poor resolution, so pinpointing the exact position of radio sources was very difficult. In 1959, the third Cambridge catalogue of radio sources was published. Under number 273, it listed a radio source in Virgo. To determine its exact position, astronomers resorted to a clever trick. Fortunately, the Moon's path passes through Virgo. Scientists observed the moment when the Moon moved in front of the radio source and temporarily blocked it. When the Moon moved slightly farther along its orbit, the signal reappeared. These observations greatly refined the position of the source. Astronomers determined that it corresponded to a small 12-magnitude star. In 1963, astronomer Martin Schmidt obtained the spectrum of 3C273 and discovered a very large redshift. It became clear that this wasn't a star at all. The distance to 3C273 turned out to be enormous, about 2.5 billion light-years. Because 3C273 was both a radio source and looked like a star, but was not actually a star, this class of objects was named quasar, short for quasi-stellar radio sources. The object 3C273 in Virgo is the most famous and brightest quasar. Its brightness is about 12 magnitude, and I have even observed it visually with my small telescope under dark rural skies. Just think about it, the light from this object travels 2.5 billion years, and yet we can see it in amateur telescopes. Professional astronomers were equally impressed. What enormous energy must such an object possess to shine so brightly from such an immense distance? Its energy output exceeds the combined light for all the stars in the entire galaxy. Various attempts were made to explain the nature of quasars and their enormous energy. Today, the prevailing view in science is that quasars are active galactic nuclei in distant galaxies. At their centers lie supermassive black holes with accretion disks. They interact with surrounding gas, accelerated to enormous speeds, heated to tremendous temperatures, and launch extremely bright relativistic jets into space. And where is the most famous supermassive black hole today? Correct, again in Virgo. Here lies the galaxy M87. It is easily visible in amateur telescopes as a faint fuzzy patch. In 2019, thanks to radio observations, the first image in history of a black hole's shadow was obtained in this galaxy. It is perhaps one of the greatest scientific achievements of the first quarter of the 21st century. But let us return to the 20th century, to that star of distinctly violet color labeled Ton 618. In 1970, at an Italian radio observatory located about 30 kilometers from Bologna, another sky survey was conducted. A scientific paper was published with a large list of objects emitting radio waves at 408 MHz. Among them was Ton 618. 3 years later, its spectrum was obtained at the McDonald Observatory in Texas. It became clear that this was a quasar, and not an ordinary one, but a very distant one. Its redshift corresponded to an object whose light has been traveling toward us for an astonishing 10.8 billion years. According to catalog data, the brightness of Ton 618 is about 15.5 magnitude, perhaps slightly fainter. It cannot be seen visually through an amateur telescope, but photographing it is quite realistic, and of course I decided to try. I went into the mountains and pointed my telescope at the required coordinates near the border of the constellations Canis Venatici and Coma Berenices. I exposed the image for only 30 minutes, and this is the photograph I obtained. At first glance, the most interesting object here is the bright spiral galaxy NGC 4414. Its light has traveled 62 million years to reach us. It was first discovered in a telescope by William Herschel in 1785. Over the past 50 years, two supernovae have erupted in this galaxy in 1974 and 2013. The Hubble Space Telescope has also imaged it twice, producing very detailed pictures. If you look closely, there are many faint smudges in my image. These are distant galaxies. One might assume that the stars belong to our Milky Way, and in most cases that's true. But this tiny star is an exception. It is not a star at all. It is the quasi-stellar radio source TON 618. Right now you can see the light that began its journey 10,800,000,000 years ago. It is difficult to imagine and difficult to comprehend, but these photons were emitted when our solar system didn't yet exist. This is certainly the most distant object in this frame, though far from the faintest. Studies of the spectrum of TON 618 and attempts to understand how such an object can be visible from so far away have led scientists to interesting conclusions. It may be one of the most massive black holes ever discovered. Estimates suggest it could be 30 to 60 billion times the mass of the Sun. For comparison, the black hole in M87, whose mass is very reliable to us, is much smaller, about 6.5 billion solar masses. However, the mass of TON 618 was obtained indirectly from the width of emission lines in its spectrum. The accuracy of such estimates isn't very high. Therefore, it's considered one of the most massive candidates, but not a securely confirmed record holder. So why did TON 618 go so viral on the internet? Probably because online audiences still love rankings, records and top 10 lists. At the same time, we tend to simplify things. Subtle scientific discussions about uncertain measurements are hardly interesting to most people, and we shouldn't ignore the power of the name itself. Its short and memorable TON 618 really does capture attention. But even if the mass and physical size of TON 618 are uncertain, the distance to this object is known and it is colossal. So I'm already happy just knowing that my photograph contains such a distant object. That's all for today. If you enjoyed the video, please like, leave a comment and subscribe to the channel. And I wish you clear skies and successful observations. See you!